Okay, so this is our first video on chapter 21, which is called Fuels and Heats of Reaction. So there are three parts to this chapter, and we're just focusing on the first one for now, Introduction to Organic Chemistry. So organic chemistry is defined as the study of the compounds of carbon. So all these molecules that you see in the background here, you might see a lot of those in biology as well. A lot of chemicals that are seen in biology are organic compounds. And we are going to be studying compounds like this. Thankfully not as complicated as these ones you see here, but along the same lines. So almost all organic compounds are covalent. So because we're talking about carbon, carbon usually bonds covalently, so sharing electrons rather than ionically. And it's very important in the study of pharmaceuticals. So anyone thinking of doing anything medicine, pharmacy, or any type of chemistry containing subject at university, this will be an important topic for you. Detergents, synthetic fibres, dyes, paints, fuels, explosives and adhesives, these are all, the foundation of all of these is in organic chemistry. So the first kind of branch of organic chemistry that we're going to look at is hydrocarbons. And as the name might suggest, a hydrocarbon is a compound containing carbon and hydrogen only. The source of hydrocarbons are from fossil fuels. These are coal, natural gas, which is methane, and methane is what we get, and this is an important thing to note down actually that I haven't written on the slide. Methane is natural gas, which is the gas that comes from the decomposition by animal waste or vegetation. So people joke a lot that methane is the gas that cows excrete. So petrol as well is the other one, coal, natural gas and petrol. And fossil fuels are fuels that were formed from the remains of plants and animals that lived millions of years ago. So the fossils have been compressed usually underwater into these fuels. So the three main classes of hydrocarbons that we have, we call them families or homologous series. These are alkanes, alkenes and alkynes. So you'll notice there you need to be very clear when you're writing out answers for this, because each one of those words only differs by one letter, so you need to be very careful. And so an alkane homologous series, an alkene homologous series or the alkyne homologous series, they're all a series of compounds with similar chemical properties. So that's a key point, similar chemical properties. A gradual variation in physical properties. So similar chemical properties means that they have similar reactions with the same substance. A gradual variation in physical properties means that it gradually varies as you go down the list. You'll have gases, then liquids, then solids, or the other way around. And they have a similar method of preparation. So the way you would prepare the chemical, how you would create it, is similar. They have a general formula where they differ from the previous member by CH2. So you'll understand that a bit more as we move through the video. So yeah, that's your homologous series. It's a series of compounds with similar properties, basically, if you wanted to make it very simple. But if you were asked to give a definition for this, you would need all of that information underlined there. So the first homologous series that we're going to look at is alkanes. These were formerly known as paraffins. I can't imagine they would ask you that, but just in case they mention it in a question, just be aware of it. So alkanes, the homologous series, all of the atoms in these molecules are linked by a single covalent bond. So therefore they are saturated compounds. And what that means is, if we look down here at this compound, we know that the lines here between all of the atoms There are bonds, and they're all single bonds. If we had a double bond, it would look like that. But we don't. Alkanes have only single bonds. And we say that then they're saturated. And to understand that, let's just quickly look at carbon. It's in group 4, so it has 4 electrons in its outer shell, like we can see here. And so that means the maximum number of bonds that carbon can make, it can't make any more than 4. So it can use each one of those electrons in a covalent bond and share it with the with an electron from another atom. So carbon could make 4 single bonds, as we see here. Carbon could make 2 double bonds to something else. It could make a single, or it could make a double and 2 singles. Any of those options are valid in the grander scheme of things, but for alkanes, it's only this one that we're interested in. They only have single bonds. And a saturated compound is one in which there are only single bonds between the atoms. Saturated, if you think of it, if you went out in the rain and you came in and you said, oh, my clothes are saturated, that means they have as much water as they could possibly hold. You're soaked through. A saturated compound is one that has as many bonds within it as possible. Hydrogen can only make 1 bond, and it's making that to carbon. Carbon can only make a maximum of 4 bonds, and it has made 4 bonds. So we have the maximum amount of bonds that we could have. So a saturated compound is one that only has single bonds. So how do we name these alkanes? So there's 2 parts to the name. There's a prefix which indicates the number of carbons in the molecule. So let's just look at that first. So meth is highlighted over here. That is 1 carbon. Eth is 2, prop is 3, bute is 4. That prefix tells you how many carbons are in the molecule. So if I told you this, if I said this is a molecule of hexane, how many carbons would you expect there to be in the molecule? You would hopefully have said 6. If I said this is octane, that would mean there's 8 carbons in it. If I asked you how many carbons are there in butane, you would say 4, hopefully anyway. So then the second part of the name, you'll notice for all of these is the same, and that's the beauty of our homologous series. So our homologous series is alkanes, so each one is an alkane, and that suffix, the end of the name, is added on, and that tells us which homologous series this molecule belongs to. So hearing the word ethane here, I know, because I've learned them off, that eth, ETH, is 2 carbons, and I know that my molecule is from the alkane series because of the ending ane. And what that tells me is not just that it's an alkane. Knowing what I know about alkanes, I should be able to work out from that all of the bonds in this molecule would be single. So the name here, this last part, the name, what it tells you is the type of bonding in the molecule, that it's single bonding because it's an alkane, and how many carbons the molecule has. So if you want to pause there for a second and try to write out or draw out the bonding in propane. Hopefully you paused there. I'm just going to draw it out for you as well. So propane, I know it has 3 carbons because prop is 3. And I know that each carbon needs to have 4 bonds. I also know that an alkane is a hydrocarbon, so anything other than hydrogen and carbon is not going to be included here. So I will give 3 more bonds, 2 more bonds, and 3 more bonds. And if I had space, I would write in hydrogen on all of those. Hopefully you get the idea. I can't fit it in around the rest of them. All of these lines that I've drawn here are bonds to hydrogen. So that's what my propane should look like. Hopefully it makes sense. Next, with naming the alkanes, is just a quick note for you. You need to learn off these prefixes. So you need to learn off meth, eth, prop, but, pent, hex, hept, oct, non, and dec for 1 to 9. The way you can do this is with an anagram. I find myself that people tend to know pentane because of a pentagon has 5 sides, hexane, hexagon, heptagon, octagon. Non tends to be associated, the letters are similar to 9, and dec, think of decade for 10. So I think the only problems that arise are with the first 4. That's why I have them highlighted there. And the anagram, is that what it's called, that I've used to learn those myself, is the one that my teacher gave me, was monkeys eat peanut butter. And the real issue occurs there is between propane and butane, and propane and pentane. So these 3 here are where I tend to see issues. People mixing up propane and butane, or people mixing up propane and pentane because they don't take a second to think about it. So I would just be aware of that. You can learn off monkeys eat peanut butter if you want, make up your own, doesn't matter, as long as you know the order that they're in. You might need a longer anagram if you don't know these, if those ones don't seem as obvious to you as I think they should. I'm probably wrong, but you might need to make up a longer one for yourself. What I'd like you to do now is just have a look at down the molecular formula list. How does it change? So here I've got 1 carbon and I've got 4 hydrogens. Here I've got 2 carbons and I've got 6 hydrogens. What have I done to each number? Going from here to here, I've added 1. Going from here to here, I've added 2. Next, I've 3 carbons, 8 hydrogens. Pen's not working. What have I done? Again, I've added 1, and this way I've added 2. So what I want you to do now is write a general formula for the molecular formula using N. So if I said it's Cn, so that there's N carbons, could you figure out what you should be writing in for the general formula for hydrogen? Hopefully you gave that a go yourself. The general formula is CnH2n plus 2. So if I test that out, if carbon is 8, hydrogen then should be 8 times 2. So I'll write it out. This should be 2 times 8 plus 2, which would give me 18. 16 plus 2 is 18. So that would tell me that if I've got 8 carbons, I should have 18 hydrogens, and that's exactly what I have. So it might be, I would recommend, instead of trying to learn off any formulas from this list over here, instead of trying to learn off any of those, I would suggest learning off this formula. Because as we mentioned earlier on, we've got alkanes, alkenes, and alkynes. And so I think it would make it much easier. You would just have one general formula for each of those rather than having to learn off a whole list of formulas. Okay, now I want you to name these 2 molecules. So see if you can write down the formula. So C something, H something, and then try to name them. Without going back and checking, and then I'm not going to give you the answer here because I want you to try to do it yourself. So write down your answer and then click back in the video a couple of seconds and check with the list to see if you got it right. So in our definition for homologous series, we mentioned that a homologous series is a group of compounds with similar chemical properties and a gradual change in physical properties. And that's what we can see in the alkanes. The alkanes, so what I mean by 1 to 4 over here and 5 to 17 means carbon 1. So the alkane with 1 carbon up to the alkane with 4 carbons. All of those are gases. Then from 5 up to about 17 are liquids, and from there on they're waxy solids. So what I want you to think of now for a second, you might pause. What happens to the boiling point of alkanes as the carbon chain length increases? And of course, the answer is the boiling point increases. So the smaller ones are gases. They have already boiled at room temperature. The middle of the way ones from 5 to 17, they are liquids at room temperature. So they haven't yet boiled, but it doesn't take long. You don't have to heat them up too much for them to boil. And then the ones from 17 onwards, they have much, much higher boiling points. So you can see that in the graph here, you can see the trend. So methane, ethane, propane, and butane, all of those have boiling points below 0. So they're all going to be gases at room temperature. Above 0, we've got pentane to decane shown on here. And those are all going to be liquid, so their boiling points are above room temperature. So the reason the boiling point increases is because the relative molecular mass increases. So each time we add on a CH2 group, we're adding on more mass. It's making the molecule bigger and heavier. The reason that this increases the boiling point is that as you increase the size of the molecule, you increase the strength of the van der Waals forces between them. And eventually they get so big and there's so many electrons in the electron cloud that we can expect that there may be dipoles, temporary dipoles able to form. And that's going to increase the strength again of the force of attraction between the molecules, so you'll need more energy to separate them. The harder you hold on to something, the harder, or the more strongly you hold on to something, the harder it is for someone else to pull it out of your hands. So as the forces of attraction increase here, the more energy you need to pull them apart. Alkanes are insoluble in water, but they are soluble in non-polar solvents such as cyclohexane. So if we were to look up the electronegativity difference between carbon and hydrogen, you would find that it falls into the non-polar category, so it's non-polar. That means that it can dissolve in all non-polar solvents, like dissolves in like, but it's insoluble in water because remember, water is polar. There's a big electronegativity difference between the oxygen and the hydrogens.